Okay, good morning to everyone. In the last class, we have discussed about the strength of a source as well as a sink. So today we are going to discuss about the strength of a doublet and how to derive the complex potential for a doublet. Okay, so here in the last class, as we have discussed about the strength of a source, if you take the source generated at a small circle form, if it is having a volume of cross section 2 pi m, in that case m is called a strength of a source. In the case of a strength of a doublet, if you take m into delta s, that is equal to some finite value, that is mu. When m value tends to infinity, then the elemental section, that is delta s, tends to 0. In that case, at this condition, mu is called the strength of a doublet. Okay. So as like the source, the if 2 pi m is the volume of the cross section covered across that circle, small circle. In that case, m is said to be a strength of a source. In the doublet form, if m into delta s, that is equal to some finite value, and when m tends to infinity, at that condition delta tends to 0, then you can call that mu, whatever the finite value you have taken, that is the strength of a doublet. And the line delta s is called the axis of the doublet. Okay, as you know, what do you mean by doublet? Doublet is nothing but it is a combination of source and sink. And here, in order to travel the doublet, we have a particular direction. We have to move from sink to source, not from source to sink. Okay. So the axis of the doublet, you have to take the direction from sink to source. Okay. And this is very important. After knowing the definition of a strength of a doublet, now we are going for the derivation of a complex potential for a doublet. As like in the last class we have derived the complex potential for a source. Now we are going to derive for the complex potential for a doublet. So before calculating the complex potential for a doublet, we have to create one doublet now. Doublet in the sense it should involve by a source as well as a sink. So here in the diagram, here we are taking a xy plane, that is two-dimensional plane. Okay, and the source is placed at a point and the sink is placed at a point of B. Okay, and the source, it is having the strength of minus m. Here the m is the source. Either you keep the source here, one should be a point of source and another should be a point of sink. Here in this diagram, the source is kept at point of B, so its strength is m, and the sink is placed at a point of A, so its strength is minus m. So your flow direction is from A to B. As I told, for the doublet, the direction should be from sink to source. Okay. So this diagram you are explaining now. Let a doublet AB of strength mu be formed by a sink minus m, which is situated at a point of A, okay, and a source which is placed at a point of B, and its point is z equal to A plus delta A, because from here to here there is a small distance, that distance is delta A. So the point of B is nothing but z equal to A plus delta A plus delta A, and here it is z equal to A. The sink is placed at a point of z equal to A, and it is having this strength minus m, and the source is placed at a point of B, it is having strength m, and at a point of z equal to A plus delta A. Delta A is nothing but the distance between A and B. Okay. So this is all about the explanation about the diagram. Okay. Then now we have to write the strength of a doublet. Strength of a doublet is nothing but mu equal to, as like the formula for strength of a doublet, mu equal to m into delta s. Now here mu equal to m into delta s is nothing but your total doublet is AB. Okay. So that's why you are writing that AB. Okay. Now, the value of delta A, whatever the distance between AB is there, that can be calculated by the result that delta A equal to AB into e to the power of I into alpha. Because in order to travel from A to B, if you draw a normal axis with the x-axis, then there is an angle of inclination, that is alpha. So this is increasing exponentially. So this whatever the distance covered is there, that is delta A, that can be calculated as AB multiplied by e to the power of I into alpha, and the value of Z is in the form of a polar form, that is R into e to the power of I theta. And here you are explaining what do you mean by alpha. Alpha is the inclination of the axis of the doublet with the x-axis. Okay, this is the inclination of the axis with the x-axis. Now, the complex potential which is indicated by W due to this doublet at any point of P of Z, or at any point in this plane, if you take a P of Z at any point, in that case, you can calculate the complex potential for this doublet, therefore this AB, that can be written as this W is equal to, as I told, doublet is nothing but a combination of source as well as a sink. So you have to write the complex potential for a source as well as the complex potential for a sink. Now we are moving from the direction sink to source. So first you have to write the complex potential for a sink. Remember the last result in yesterday's class, we have derived the complex potential for a source, that is Z equal to minus m log Z when it is placed at a origin. Okay. If you are writing the complex potential for a sink, in that case it becomes minus m log Z. Okay. If for a source it is minus m log Z. For a sink it is minus of minus, it becomes plus. So that m log Z. So first you are writing the complex potential for a sink now. Okay. So here it becomes m log Z. When it is placed at the origin, then you used to write only Z. But here the point is mentioned here, Z equal to A. So it becomes Z minus A. Okay. Now go for the source. So for this, the complex potential for a source. So complex potential for a source, and it is placed at A plus delta A. So it becomes minus m log Z minus whatever the point is there, that point you have to write. If it is placed at Z1, then it becomes Z minus Z1. If it is placed at A, then it becomes Z minus A. Instead of A, here it is A plus delta A. This is the point. Okay, I repeat. This is the complex potential for a doublet, and in order to write the complex potential of a doublet, you have to write the combination of complex potential for a sink as well as complex potential for a source. Now, first we are writing the complex potential for a sink, which is placed at a point of Z equal to A, and it is having its strength as minus M. Now, according to the formula of complex potential for a source, you know that it is minus M log Z. Now, you are writing the complex potential for a sink. So, it becomes plus M log Z minus A. If it is placed at origin, in that case, no need to write A. But here, the point is particularly mentioned. It is placed other than the origin. So, that's why we are writing M log Z minus A. Next, you are writing the complex potential for a source. So, it becomes minus M log Z minus A plus delta A, because the source is situated at a point of A plus delta A. So, we have added the complex potential for a sink as well as the complex potential for a source. Both the values we have written now. So, now together it becomes the complex potential for a doublet. Then now remaining quantity is nothing but just a arrangement in a systematic way we are arranging now. So how we are using? So among these two results we are taking minus m as a common term. So when you take minus m as common, then it becomes, this term will be positive, m log Z minus A plus delta A, this will be positive and this becomes negative. So it will be in the form of log m minus log m. So you can write that minus m log m divided by n. M is this term and n is this term, Z minus A. So P by Q form or M by N form. So Z minus A minus delta A, when you multiply negative inside the bracket, then you will get Z minus A minus delta A divided by Z minus A. Now you are splitting it. So Z minus A divided by Z minus A, so it get cancels, it remains it as 1. So 1 minus delta A divided by Z minus A. Okay. Now, you know the binomial expansion of log of 1 minus Z minus log of 1 minus Z. The expansion of minus log of 1 minus Z is nothing but Z plus Z square divided by 2 plus Z cube plus Z cube by 3 plus so on. So use this result for this. In place of Z, you have delta A divided by Z minus A and neglect the higher order. Okay. So when you neglect the higher order term and consider only the first digit, first place value, that is Z, in place of Z, our result is nothing but delta A divided by Z minus A. So here you will get minus, which is there inside this expansion itself. So it becomes m into delta A divided by Z minus A. But already we know the value of delta A. Delta A is nothing but AB into e to the power of I alpha. So instead of writing delta A, we have written this as AB into e to the power of I alpha divided by Z minus A. Okay. So we got the total result as m into AB into e to the power of I alpha divided by Z minus A. Further, we know that mu is nothing but m into AB. So, in place of m into AB, we can write the strength of a doublet, that is represented by a symbol mu. So, it is mu into e to the power of I alpha divided by Z minus A. So, total result we can write that W equal to mu into e to the power of I alpha divided by Z minus A. This is the standard result which we call it as a complex potential for a doublet, which is very important. As in the last class we have derived the complex potential for a source, that is W equal to minus m log Z. Here this is the complex potential for a doublet, that is W equal to mu into e to the power of I alpha divided by Z minus A. Okay. So very simple form it is there. First you are writing the sum of the complex potential for a sink and the complex potential of a doublet source. Then together we are arranging it in the form of a P by Q form. Then you are splitting it and you are taking the expansion of minus log of 1 minus Z. In that quantity you are neglecting the higher order terms. You are only taking the first order. So that is Z. Z in the sense your Z is delta A divided by Z minus A. So the value of delta A divided by Z minus A is written here. Delta A value is replaced by AB into e to the power of I alpha and m into AB is nothing but mu. That is nothing but your complex potential for a doublet. Okay. Now we have some standard results. Okay. So you can see here, if the doublet is placed at a point of origin. So here, whatever the derivation you have done here, this shows that the doublet is not at the origin. Somewhere else it is. Z minus A in the sense it is away from the origin. Okay. Now what we are imposing one condition in this is, if the doublet, the point of AB, this AB point, if it is kept on the origin, okay, source and the sink, instead of A point and A plus delta A, if it is placed at the origin, in that case there won't be any creation of an angle, because both the source and the sinks, they are lies on the origin, so that alpha will be 0, okay, and A will be 0 because there is no distance between source and sink. Okay. In that case, your complex potential will be mu into e to the power of alpha is 0. So it is e to the power of 0 is 1. So divided by Z. Z minus A value is 0. So that you will get W equal to mu divided by Z. This will be the complex potential for a doublet when you are keeping your doublet at the origin. That is a special condition. The same thing is here. W equal to mu by Z. And the second condition is, if the axis of a doublet is along x-axis, then we can write W equal to mu into e to the power of I into 0 divided by Z minus A. If it doublet is along x-axis, initially your doublet is like this. Now what you are doing, instead of in an inclination, you are keeping your doublet along the x-axis. In the sense, source and the sink, both they are lies on the x-axis. If they both lies on the x-axis, in the sense there is no creation of an angle, so alpha will be 0 but the distance will be there. So because of that, what you are writing, that is mu into e to the power of alpha is 0, so it is e to the power of 0 is 1 divided by z minus a. So it is mu divided by z minus a. This is the case when the doublet is along x-axis. Okay, and if there are number of doublets, means you are having n number of sources, n number of sinks, in that case you can also write the n number of doublets also. So in general you can write that, that is mu 1 divided by mu 1 into e to the power of I into alpha 1 divided by z minus a1 plus mu 2 e to the power of I into alpha 2 divided by z minus a2, so on. How many number of doublets you are having, all the doublets to be added. So in general we can write that summation as n equal to 1 to infinity mu n e to the power of I alpha n divided by z minus a n. Okay, this is a generalized form. How many number of doublets you are having, those many number of complex potential you can write it. As like the last class we have written, if there are n number of sources, in that case we can write that mn log of z minus a n if it is placed other than the origin. Okay, like that you can write the general form. Okay, so this is the one part, one section, means how to write the strength of a source, sink as well as the doublet, and how to calculate the complex potential for a source, sink and doublet. Now we are going for the another section, that is image of a source, image of a source, image of a sink, image of a doublet. Then what will be the complex potential for a image also? Okay, that result we are going to discuss now. So in a simple language, whenever you are standing in front of a mirror, then your real body is nothing but a source, and whatever the image, your image you are seeing in the mirror, that is nothing but your so pre-image, that is not a real part, that a virtual image you are getting. Okay, see here also, if you are lighting one candle. Okay, candle in the sense whatever the image it is coming, that is in the form of a shadow. Okay, if your object is there in a white section, simple language in the sense, whenever you are moving in a summer season, whenever you are walking, you will see your shadow on the earth, that is nothing but your image. So here also, in if you take one core, one side of the core, if you are keeping one source, in the sense on the other side the same source, it will have its image also. So, if you want to write the complex potential for this core, in the sense, you have to consider the source sink as well as its images on the other side of the core. Then only it completes the total complex potential. Okay, that part we are going to discuss now. Okay, so first we will see what do you mean by image. If there exists a curve, consider any shape of the curve C on the xy plane in a fluid such that there is no flow across them. So whatever the curve you are taking, on that curve there should not be any flow. Curve should be a stationary and it maintain it as a constant level such that there is no flow across them. The system of sources, sinks and doublets on the side of the core is said to be the image of the source, sink and doublets on the other side of the core. A core is missing here. Okay, so one core is there. Let us consider this as a core. This part is nothing but your core, and your source sink is there on this core. Okay, there should not be any disturbance now. Okay, when so you kept your source as well as a sink, in the sense together you can call this as a doublet, and this is involved by source and sink. On other side of the core, this source and sink, it is having its images. Okay, so it is having source image, sink image as well as doublet image. Okay, so all the parts it is having. So how it is, we will see by taking one diagram here. So here you can see the source is at a point of A. Here capital A is there. It is missing here. and this a, it is having a point of distance as a comma 0. Y coordinate is not there, so it is 0. So when you are keeping your source in the sense on other side of this plane, this is xy plane we have considered, on other side of this plane it is having its image in the sense only the distance, whatever the distance is there, that will come in the form of a negative, but the strength is having the same thing. Either you consider the source strength or the sink strength, the whatever the strength capacity is there, that term is carried same, only change in the distance axis. Okay, so if your source is kept at the positive axis, the image is created at the negative axis, so only the distance symbols will change. So here the source is kept at a point of a, capital A, and it is having the coordinate small a comma 0, and this point is having its image on the other side of the plane, and its axis is nothing but minus a comma 0. Whenever you are writing the image strength of the source, then you used to write minus m log z minus a, because the place is nothing but z equal to a, so it is z minus a. The same thing is written here also, minus m log z minus here the position is minus a, so it becomes minus of minus plus, so that z plus a. Okay, so this term we are going to discuss now. So here the theorem, what it is telling, find the image of a simple source with respect to a plane. Here the plane we have taken it as a straight line in a xy plane, and show that the image of a doublet with respect to a plane is an equal doublet symmetrically placed. So whatever the image of a doublet you are calculating, that should be a symmetric to the reality. Okay. So first, according to the diagram, we are explaining now. So first, place a source M at a point of B of minus a comma 0. In this diagram, the source is kept at a point of B and it is having minus a comma 0. Then the complex potential at P due to this system is given by. Okay. So one second. Okay. Source is placed at a point of B and it is having the coordinate minus a comma 0. Then the complex potential at P due to this system is given by. So you are standing here and you are calculating the complex potential point at a point of B, and it is having its image on the other side. Okay. Not necessary that you have to keep your source on the positive axis only. No, not like that. Wherever you are keeping your sources, on the other side, on the opposite side, it will have its image. Okay. So here the source is kept at a point of P and it is having its image on the other side. It is nothing but a comma 0. Now you are writing the complex potential from a point of P. So resulting complex potential you are writing. So that W equal to minus m log z minus a. First we are writing this point, so that z minus a minus of m log z minus of minus a, so it becomes plus a, so z plus a. So total value, if you take minus m as common, then you will get log m plus log n form, so that you can write log mn, so that minus m log z minus a into z plus a, or else also you can write in another form, z minus a into z plus a, also you can write z square minus a square. Okay, as you are convenient. So our intention is to minimize this result and we want to write a standard form. So W equal to minus m log z minus a, you are writing in the form of e to the power of I into theta 1, and z plus a you are writing in the form of I into theta 2. The two angle of inclination is created, so that you can write together it is minus m log r into e to the power of I into theta 1 and r2 into e to the power of I into theta 2, where the axis of PA, P to A, he is making an angle of theta 1 and the axis of P to B is making an angle of theta 2, like that. and the radius is r1 and r2, so that you are writing minus m log r1 e to the power of I into theta 1 and r2 into e to the power of I into theta 2. So r1 r2 take it as it is as a product, so that you are writing exponential value e to the power of I into theta 1 plus theta 2. Now, when you go for the expansion, that is log r1 r2 into e to the power of I into theta 1, once again you split it. So it is in the form of log mn. When you split it, it becomes log of r1 r2. Take that term as one term. So it is log r1 r2 plus log e to the power of I into theta 1 plus theta 2. So log e to the power of I into theta 1 plus theta 2, it is along with the logarithm. So log e to the base of e will be 1. So it becomes I into theta 1 plus theta 2. So you will be having the result as minus m log r1 r2 plus, and outside minus m is applicable for both the values. So it becomes minus m into I into theta 1 plus theta 2. Now w is written as 5 plus I side. Now you equate the real part and the imaginary part, you will get. So first real part is 5. 5 is nothing but minus m log r1 r2, and psi is nothing but minus m into theta 1 plus theta 2. Okay. So now if p lies on the y-axis, when the point P, it is like in the triangle form, this point, if it is lies on the y-axis in the sense perpendicular form, if it is lies on the y-axis, in that case the angle pi is equal to theta 1 plus theta 2, either it may be equal to 180 degree, the sum of two angle it is equal to 180 degree, or else pi equal to theta 1 or theta 2. Okay, any one condition should be satisfied. So from equation 1 and 2, whatever the result you got, that is xi equal to I minus m into theta 1 plus theta 2. And the second result you told that when p value lies on the y-axis, in the sense theta 1 plus theta 2 should be equal to 180 degree. Use this condition and substitute here. So it becomes xi equal to minus m into pi. M is nothing but a strength of a strength of a source, and pi is nothing but a constant value. Strength is also a finite value. When your finite value is multiplied with the constant value, you will get it as again a constant. That shows that y-axis is a streamline, and hence the image of a source m at a point is a source m at b point. Only change in the position a comma 0 and minus a comma 0. That is to say that image of a source with respect to a line is a source of a same strength situated on the opposite side of the line at an equal distance. So whatever the result you have taken, at the end you have proved that the streamline existing, which is again a constant value, that shows that either you keep the source on the positive axis or the second negative axis, whatever the image you are getting, that is again it is having the same strength, it is carrying the same strength on the opposite line, and at that line is kept at a distance, equal distance from the source. Okay, this is all about the image of a source. So in the today's assignment, you write the complex potential for a doublet and the image of a source. So tomorrow we are going to discuss about the image of a doublet. So today you practice these two results.